6. Sir, you may proceed with the talk. We are ready.
Okay. Okay, good afternoon, everybody, and it's my pleasure today to be with you online. I apologize not to be in Belgium, and I appreciate that you are attending my presentation entitled The Design of Reunited Telomers for Well-Architectured Fluoropolymers and Applications. So this means that in this presentation, we are going to I'm going to give you some advice on how to proceed on the telomerization, which are the different chain transfer agents, and also what can we do with these telomers which have been produced. Of course, I will give some applications in this area and conclusions. So what is telomerization? Telomerization is a reaction between a chain transfer agent and a monomer. Let's consider VDF, vanillin fluoride. This reaction, in the presence of radicals, it's a radical telomerization and leads to what is called the telomere. As you can see, the chain transfer agent has a weak bond from which the end group are going to be located at both ends of a chain. So this is very interesting because if you choose adequately the transfer agent, you can prepare what is called telecalic compounds or alpha-omega difunction. So this chain transfer agent behave as radical systems in order to promote the oligomerization of the monomers. Let's say usually when you have a double bonds, you have a pi and sigma bond, and the pi bond is open while the sigma bond is remaining. Telomers usually are low molecular weight polymers, but they are functionalized, and the N can range between 1 and, let's say, 50. So it's very difficult because of the presence of a chain transfer agent to go to very high molecular weight. So regarding the XY bond, you can consider CH, just like in methanol, where you have a CH bond on this side, not BOH, or chloroform, CH, or sometimes CCl. But it depends on the chain transfer agent. pH also can be used, and I will give you an example on diethyl phosphonate. Sulfur also are required, so they stink a lot, but they are very efficient in thermalization, and usually they lead to monoadduct or diadduct. SiH bond also can be cleaved. Sulfur-sulfur, so we did some example with disulfide or this specific sulfonate containing sulfide, and carbon halogen, carbon chlorine, carbon bromine, in the case of fluoropolyethers, bromine. So in Solvay, they did some thermalization with this kind of chain agent, and also carbon iodide and diodide. The radicals can be generated either photochemically or thermally, or via electron beam, or by redox catalyst, copper chloride iron chloride, or radical initiators. So I will give you in my presentation several examples of these systems. And what are important to find is, indeed, if you are looking at, in collaboration with a company, of course, the company is very interested by the yield, by the degree of thermalization, the number of N, the chain transfer constant, which is the ratio of the transfer rate to propagation rate, and also the defects of VDF in the case if you take VDF. And in my previous presentations, I mentioned that when you have a macroradical reacting, it had a possibility to react either onto the CH group or the CF2 group, so that you can have what is called a head-to-tail addition or a head-to-head addition followed by a tail-to-tail addition. So keeping that in mind, I'm going to give you some examples of a different chain transfer agent. Let's consider first with a pH and diethyl hydrogenophosphonate. So this reaction was carried out, initiated by Teshmuti peroxide at 140 Celsius. And when you look at the total product mixture of what you observe after a couple of hours, you see that you still have some remaining chain transfer agent. And then you have a classical telomeric distribution in which you observe the monoadduct, diadduct, triadduct, tetraduct, etc. So in this case, you can see you can go to the adducts, and by what is called the David and Gosselin's law, I don't have much time to do that, but if you measure the area under the signal toward the sum of the areas, plotting on versus the ratio of chain transfer agent concentration and the monomer, it's possible to have some straight lines, the slope of which give you what is called the CT1, CT2, CT3, the other direction, okay? And to go to a kind of infinite CT value, showing that in this case, the chain transfer constant is 0.34 at 140 Celsius. This means that the propagation is much higher than the transfer. So consider this transfer agent is not so efficient in thermalization. The yields were good, but in this case, if you start from 1 to 1, you will get about a dP of 7. Okay, so this is rather interesting, and we published this work a couple of years ago. Now, another example is if you consider CCl3Z in thermalization of VDF, Z being either H for chloroform, Cl for tetrachloromethane, or bromine for trichlorobromomethane. And as you can see, when you consider the slopes regarding the ratio of CTA to VDF, you can see that also in the three cases, you have a straight line, and the slope are totally different. If you consider CCl3Br, you can see the slope is about 26 or 34. Here in the case of CCl4, the slope is much lower, reaching 0.25. And in the case of chloroform, is even lower, with a CT of 0.06, all of them at 140 Celsius, showing that the CCBr is much weaker than CCl and much weaker than CH, which was a little bit expected. But this is interesting because if you use the Meyer's law, it's possible to, from the ratio, the stoichiometry of transfer agent to monomer, and from the CT, it's possible to tune the degree of telomerization N in this case. These results were very interesting, and even with colleagues at the University of Sherbrooke, we had a nice collaboration 10 years ago regarding the simulation. And our colleagues in Sherbrooke studied the relative energy versus the reaction coordinate regarding the addition onto CF2 or onto CH2. You remember I mentioned at the beginning that you can have some head-to-tail addition or head-to-head addition. And it's very well seen here that the reactive energy in a macroradical reacts onto CH2 is much lower than that reacting onto the CF2 of VDF, showing that in the propagation step, usually this radical addition onto the CH2 of VDF is favored. And even our colleagues were able to measure the energy versus the reaction coordinate regarding CCl3Br, showing that you have a very low energy, so the chain transfer is favored, or CCl4 or even chloroform, which has the highest energy, so that the transfer toward the growing radical is favored for CCl3 and less favored for chloroform. So these concepts were very useful for us in order to well explain how the mechanism of telomerization. And even when you look at the literature, we try to understand what's going on regarding the recombination. And as I mentioned in a previous talk on Friday, usually the mechanism of termination occurs by recombination and not by disproportionation. But in the case of the use of radicals, freenated radicals, just like CF3, usually we favor the recombination of macroradical rather than the primary recombination. This means that you have this growing radical reacting onto the primary radical released from the chain transfer agent. And indeed, when you look at the efficiency of the CF3, I will mention how you can generate CF3, the CF3 radical onto VDF. This is much favored than the addition onto the CH2, since we evidence that, I don't go in details, by free NMR, but we didn't see the presence of these CF3, CF2 N groups in this case. So this was very interesting, and this confirmed the work of Tede and Walton when they consider different freenated radicals onto VDF or trifluoroethylene, showing that you have a very high selectivity of the freenated radical onto the CH2, you know, 1 for 0.032 onto VDF, onto CF2. And this is even worse when you have a more bulkier radical, freenated radical in the system. And here it's GEM trifluoromethyl, which has a very selective addition onto the CH2. However, in the case of trifluoroethylene, it's not so obvious, but you have this radioselectivity, and even you can you can have the possibility to get this addition of freenated radical onto the CF2. And this was very well evidenced also by polymerization or copolymerization of trifluoroethylene, in which you have a lot of reverse additions, much more than in PVDF. So the use of CF3 had different sources. And in the case of the thermalization of VDF with CF3I, after reaction and purification, we decided to do some free NMR. And I think this example is interesting because free NMR enables to determine the number of VDF units. And this spectrum is quite clear. What can you see? You can see the CF3N group in which the signal shows a quintet. And this is surprising because usually the CF3 is coupling with the CH2, the furin coupling with, and the furin is coupling with this furin in the beta position. But amazingly, the coupling constant G3FH is the same as that of G4FF, 10 Hertz, giving the presence of the quintet. So this is very nice because this is also a nice label in order to determine the amount of VDF, in which you can see the signature of the head-to-tail addition, and also some reverse addition, which is high field shifted okay, showing that you have these units. So if you consider the number of the integrals of these signals divided by 2 for a VDF over the integral of this signal divided by 3, because you have 3, it's possible to calculate the number of VDF. This signal is also very interesting because you have the N group, CF2I here, which is very conventional. So at minus 40 ppm, you can see this N group. And again, you have this match with a value of 2 and a value of 3 compared to that. So by calculating this from NMR, it's possible to have 11 units. But our scientific point of view was also driven by finding other techniques of characterization. And the other one was the Malditov. And indeed, when you look at the MALDI spectrum of the same telomere, we have a very nice distribution showing that you have a certain control. And you remember that yesterday I spoke about control radical polymerization, especially iodine transfer polymerization. And this is also the nice evidence that we have a control with a rather narrow dispersity on by MALDI. You know, you can be surprised to see a dispersity of 1.17 because we have a low value of VDF, of course. And but this is a value obtained by the resolution of the MALDI spectrum. Interestingly, the difference between the signals is 64, which is assigned to the molecular weight of VDF. And if you consider, let's say this is the 10th, so 5, 6, 7, 8, 9, 10, 11, 12, etc. So the average degree of polymerization is here is about 11, as we found by NMR. And I was very happy that in collaboration with Dr. Ladavière in Lyon, when she came to give us a talk, we could match the results of DPN value with those of NMR. So this is a very nice example. So this telomerization of VDF with monoiodo can be also extended to diodo. And in this case, we choose this diodo C6F12 telomerization of VDF in order to prepare iodine PVDF-I. And in this case, we are approaching ITP, iodine transfer polymerization, because it depends how much ratio you put. Because it's very efficient, and as I mentioned yesterday, the growing radicals can undergo transfer by the iodinated group in order to promote some dead chain with iodine, which immediately, because of a low bond dissociation energy, CF2I, possible to go back to growing radicals. And in this case, we had a different NMR spectra. You can see again the signature minus 92 of head to tail VDF. You can see also the N group coming from the reverse adducts. And here, this is also the signature of the freenated interchain. Okay, here. So we have the C6F12, which are very nice label also to determine the molecular weight, 1200. 2200, 4800, and 2700. And this, of course, depends on the stoichiometry of the amount of VDF versus the diodo. This was very interesting, and for us, we wanted to see what's going on regarding the reverse adducts. And when you see with a low molecular weight, we don't have some reverse adduct, because in this case, the control polymerization for low molecular weight does not favor some reverse addition, as seen here in the case of high molecular weight, 12,000, in which we can see some reverse addition here, the head-to-head. And as we can show in this table, regarding the molecular weights and the defects of chaining, you can see that we have almost negligible defects for low molecular weight, while we have about 7 for much higher molecular weight. 7 is a maximum. Let's say in the literature, if you consider some PVDF commercially available products, you will see about maximum 8% or 9%. Okay. And this plot represents the evolution of the defects versus the molecular weight. The thermal properties of these different products, this is not really those which have been presenting in previous slide, but we wanted to show how the importance of the telomers versus the thermal properties. And considering 7 units, we have a very poor thermal stability because we have a vaporization of the products and not a decomposition. In contrast, with 34 units or 48 units, you can see what you have a much higher thermal stability. And of course, if you have some about 200,000 or 700,000, you will go up to more than 400 in decomposition. This is the heating rate. This is on the air with a heating rate of 10 degrees Celsius. So we recently synthesized for specific collaboration these 3 different telomers, iodo-telomers, mono-iodo or di-iodo. The MALDI also was interesting in this case, and if we consider those containing the di-iodo, we can see a very nice distribution also in which we have 64. I'm sorry for that. Unfortunately, I couldn't get a full screen, but this is 64 between signals. We have a nice also SEC trace, 1.27 for 34 units. This SEC is done in THF with refractive index, so you have a negative signals, as I mentioned yesterday. And even this can be also done for the thermalization of these telomers, or VDF with these telomers. The di-iodo containing 1 unit on one side, or 2 units on both sides, or even 2 units on the same side. And even we could be able to do some thermalization. So it was interesting because it was possible to go further in this thermalization, and even with a di-iodo containing HFP, either mono HFP or di HFP, it was possible to make some chain extension of VDF. I cannot say it's a block copolymer because we have very low amount of HFP. HFP does not homopolymerize. So, of course, in the first step of thermalization of HFP, it was possible only to have 1 monoadduct or 1 alpha or beta diadduct. So these new telomers of HFP could be able to be used as chain transfer agent for further telomerization of VDF. So now I would like to go a little bit deeper, and I'm going to speak about the collaboration we had on iodine transfer copolymerization of VDF and perfluoromethyl ether. You remember yesterday, and I want to thank my co-workers. Yesterday I spoke about this IETP this was pioneered by Daikin, and this is the first patent of 1979. Trying to find out thermoplastic elastomers with the first block based on soft segment, which was also used as a new chain transfer agent for second block, in which there was the insertion of a hard segment. And as you can see here, this SEM sketch show the different crystalline zone and amorphous zone because of the different blocks. So the diel commercially available from Daikin or Viton, from DuPont or Chemours, or Techno from Solexis. So we had in this case a nice collaboration with DuPont Performance Elastomers in order to do some ITP of VDF and PMVE in water. It was nice challenging, initiated by persulfate, and to make these new products containing VDF, HFP, and also the C4F8 was very interesting as a label in NMR. So we changed the different molar ratio between VDF and PMVE, and also the content of VDF initiator in order to have a living system. And we use this persulfate as a water-soluble initiator, and of course the process was in aqueous medium. And what happens is we characterize the different co-products by MALDI, and in this case it's a little bit more complicated because PMV does not homopolymerize, but as soon as you have one unit, you can have several units of VDF. So 1, 2, 3, the green, 4, 5. I mentioned that yesterday. Also, we saw that we have a living systems regarding the evolution and the narrowing of dispersity according to the conversion of VDF. We have a linear dependence of molecular weight versus conversion, and also the thermostability depends on the molecular weight. So these compounds were very useful because the presence of diiodo at the end of a chain could be modified into functional group, just like alcohol, carboxylic acid, or even allyl derivative or trioxysilane. So we have been able to produce these telekinetic compounds for various applications, especially elastomers, low TG values. This was a target also. And as I mentioned recently, the diiodo compound could undergo some chemical modification, bisacetylation, oxidation, acrylation to prepare some telekinetic acrylate, which were photo cross-linked. This is the apparatus we have in the lab, in which you deposit on a substrate. It can be steel, it can be Teflon, whatever you want. You deposit your viscous solution, and then by photopolymerization, of course, you need a photoinitiator. We could make some cross-linking system as this kind of elastomeric films. The second strategy was to add this diiodo compound a radical way onto allyl alcohol to make this bisiodidrine, which for which the iodine was reduced with tributyl tin hydride and then acrylated in order to promote this alpha omega diacrylate. And this strategy was much better and more efficient with better yield, but this was because we had some bottleneck in this oxidation reaction leading to some dehydrofurination. So the other way was to change this diiodo compound and to react radically with tertiary peroxypivalate as initiator onto vinyl trialkoxysilane to make this telechelic trioxysilane. The yield was good, and after hydrolysis and condensation, it was possible to make a network. I apologize, it's a little bit small, but indeed you have some silicates which were embedded in the polymeric poly-VDF perfluoromethyl vinyl ether. So we have been able to propose a wide range of different compounds, can be trioxy or dietoxymethyl or monoetoxy. So it depends on the nature of the compound you use here. The hydrolysis was carried out under acidic catalyst, just like metal sulfonic acid or hydrochloric acid or trifluoric acid. The backbone, we had different polymer backbone in different content and molecular weight of VDF and PMV. And of course, we had to optimize a little bit the presence and the use of solvent in order to favor this condensation. So I don't go in details because I have so many information to give you. We characterize this specific cross-linked material by DSC to measure the TG, by TGA, by SEM, dynamic mechanical analysis, and of course we were investigating the swelling, which was very important for aeronautic applications. And indeed, this project with DuPont was very challenging because there were 6 patents, and what was very important is to find out low TG, high thermostability, and also almost no swelling. 5% swelling was fine, which was the maximum to reach. And from that, you can see that we could prepare some telekinetic trioxysilane or methyl bis-ethyl-silane or B-methyl monoetoxysilane. And even we did some co-condensation between the dietoxy-methyl-silane and monoetoxy dimethylsilane here in order to go in different catalysts and conditions. So this was nice. We had a lot of results, and indeed, from this application, the best system was to find out this monoetoxy and dietoxy, to change the ratio also, so you can imagine how many attempts we did in this work to use or not some methylated ketone, different acids, methanesulfonic acid in different concentrations, setting time. It was a little bit long, 70 hours, but the good thermostability and the TGs were, let's say, could be improved. The best one was -35, but for DuPont, this was a little bit high. However, the swelling were very good, 24 hours at room temperature, negligible, and when you heat it up at swelling of octane for 24 hours, it was good, lower than the threshold. So we could prepare some monoliths, and they were very soft, as you can see, because of the TG, but let's say not as satisfactory as we expected. However, by using this pentafluorophenyl borane, it was possible to improve significantly the condition, and also adding some few amount of tetramethyl disiloxane, which brought some softness also. So in this case, we have some nice, almost transparent, a little bit hazy material, which were very soft, in which we could see some PDMS rich phase brought by this N2H, and the TG was -47, which was a very good achievement, and the T10, the 10% decomposition at 320 under air. And the swelling boiling octane for 24 hours was ranging between 2 and 10%. So thanks to these characteristics, we could we were very satisfied, and also the DuPont company was satisfied, and deposited a patent in this way. So this is very interesting, and of course I can speak for hours regarding thermalization of VDF, but also we did thermalization of HFP, as I mentioned before, and also trifluoroethylene. And in this case, the idea was to make some solvent for lithium-ion batteries, because I will explain later on. It was possible to direct. There are different strategy and systems for lithium-ion battery. You can have liquid electrolyte, in which the salt has to be dissolved in a solvent. And in this case, we try to figure out if these telomers of low molecular weight could act as a nice solvent for salts. And the idea was to use some phosphorus because it's flame retardant. And as you may know, on liquid electrolyte for batteries, there are some issues of fire. And the presence of phosphorus enables to increase the fire resistance. So our strategy was to try to find out, was it possible to make a monoadduct of trifluoroethylene with this dimethyl hydrogenophosphonate? And the answer is yes. We don't have excellent yield, okay, it was fair, but what was interesting for the monoadduct, of course, we put a large excess of that, and then we distill. We could see that we have the presence of two isomers, so showing that, as I mentioned before, you have not a ratio-selective addition of a phosphorus radical onto the CHF, but it presents also onto the CF2. So in this case, the proton NMR was very nice and could be well identified, for instance, showing the HA and HB showing characteristic signals here and here. And we have a nice example here for NMR of an organic solvent, which was very good to dissolve the lithium salt, which was TFSI, and we published that a couple of years ago, showing also that the residue of distillation had also some telomeric distribution. So we wanted to go a little bit further and to see if it was possible to make telomers of pentafluoropropylene. So pentafluoropropylene is a very tricky monomer. Not so many reports have been published, And indeed, this does not homopolymerize. And it was used maybe 50 years ago in order to try to compete with copolymers of VDF and HFP. But because of the price of this PFP, linked mainly by the small production compared to that of HFP, they gave up the strategy to propose some elastomers based on VDF and PFP. So Hazeldine did some work, you can see, many years ago, and showed that by UV at the 7 days, it was possible to release some CF3 radical reacting onto this adduct, and then the transfer led to this monoadduct. So it's a very highly freenated compound. Okay. And of course, VCF3 reacts again onto that. So when you release, this is a very good example, because when you generate from the freenated radical, you generate the iodo-freenated compound, the CF3 issue from chain transfer agent is generated again to react again onto that. So usually the reaction, the telomerization reaction are very good. And we did some reaction a couple of years ago with my friend George Kostov, and indeed, again, we could see that there was some no ratio selectivity of perfluorinated radical onto the CF2 or onto the CH-CF3, and we released both radicals which were able to go to the products. So but the yield was very, very low in this case. And indeed, it was much better to try to do some copolymerization with PFP, for instance, with trifluoropropene. And during the polymerization, we saw that the initiation was more efficient from the perfluorinated radical onto the CH2 of the trifluoropropene rather than onto the CH2 of the CH-CF3, because of the steric endurance first, and also because of the nucleophilicity of CH2 of trifluoropropene. So this was also a second example I wanted to mention, that not only VDF, but also many other products. And this paper also summarized all the different attempts we did regarding the use of VDF, trifluoropropene, and even acrylate in copolymerization or terpolymerization with this PFP to have different telomers here. So just go back to this paper if you're interested by pentafluoropropylene. The telomerization of trifluoropropene also was interesting. And if you look at TFP, so trifluoropropylene, which we did a lot of work on that. We had a collaboration with Greylake's company, and even we published a book chapter a couple of years ago. So we did some co-telomerization with VDF and with different chain transfer agent. It was even possible to make ethylene and capping, and then to go to fluoroalcohols or fluorinated mercaptans. And even we make some diblock co-telomers in order to make amphiphilic products. We have also, of course, in telomerization of TFP with perfluoroalkyl iodide, we prepare this intermediate, which could be changed into steps in allyl derivative, and then to make some surfactant by adding some thiol, for instance, or even in capid, added VAC, and to prepare a wide range of different products. So this is a little bit ahead to my presentation in applications, but as you can see, you can play a lot, and you can do a lot of work. And we have been fortunate because we had some projects for which the investigations were very deep. Of course, all the different intermediates and products were characterized by NMR. Okay, and this gives me the transition to the use of telomers to obtain well-architectured fluoropolymers. Maybe I will take some example with EDF, because we have very strong example here We have been able to, as I mentioned before, to use some solvent for lithium-ion batteries. This was the phosphorus containing trifluoroethylene. We also make some surface modifiers, especially in photo cross-linking of derivative of acrylates. We also make some fluorosilicones, piezoelectrical device, fluorosurfactant, macromonomers, nanocomposites. Of course, today I don't have the chance to give you all the different details in these different aspects. But you can see the list can be, this is non-exhaustive because you can imagine that it's possible to do some pigments. You can prepare some smart additives. You can prepare some specific intermediates, acrylates for polymerization, etc. My first example is on fluorosilicones. And I would like to come back again, I mentioned that yesterday, on regarding the catastrophic accident in Challenger in January 1986, where after launching, unfortunately, there was an explosion because the O-rings were made of polysulfides and not fluorosilicones or fluoroelastomers. And this is a Nobel Prize in physics, Professor Feynman, who makes the test of the brittleness by adding these O-rings in the cold water, showing that they immediately broke because the TG was not low enough. And obviously, when you look at the different elastomers, what happens is you have, of course, the volume of production depends on the price. And for polybutadiene, polyisoprene, EPDM, polyisobutylene, polyurethane, these are made in a high amount. And so the price, also because of the monomer, much cheaper than in the case of fluorosilicones, fluorocarbon elastomers, hybrid fluorosilicones, or freenated thermoplastic elastomers. So this shows that, of course, the performance of the fluorosilicones are required, especially in aeronautics or in car or in engineering. Of course, you have to put the price, and fluoropolymers can be the most drawback is, of course, the price. But the price means also durability. And just imagine if you have to change an O-ring in an engine of a car, that you have to debuild all your engine to change your O-ring and then to rebuild your engine, taking time and cost. If you have an O-ring which is durable and resistant and heat resistant to solvent, etc., you have to change maybe every 10 or 20 years. So you don't have obsolescence in this on this way. However, changing a polyurethane O-ring or a PDM can be cheaper, but you have to do the work every year. And in this case, you have to pay the manpower to change the engine. So another requirement is, of course, the heat resistance and the solvent resistance. And the best candidates are in the top right, just like, and the fluoroelastomers, where Albert Van Cleef was working for DuPont and published a very nice article, okay, more than 30 years ago, but this is very interesting in this way. And what happens is, so these requirements are very important. And if you look at the comparison between the main fluoroelastomers, so usually you can have some VDF, HFP elastomers, just like Viton, Technofluorodiol, or even AFLAS, but the TG is not so high compared to that of elastomers, but still very too high also. So the copolymers of TFE and perfluoromethyl ether do not have a low TG, while the copolymers of VDF, HFP, TFE, which is called FKM also, or THV, -16, but fluorosilicones and fluorophosphazine show very interesting low TGs. And this was also a challenge to find out some alternative of fluorosilicones and even to make much better fluorosilicones. So these are the different examples of O-rings, packaging, and gaskets and specific system shafts, etc. And as you can see, in this case, you have a lot of transmission fluids, also based on elastomers, as well as sealants and gaskets. And the TGs, of course, are very important. I mentioned that before. But the idea was in this project was I tried to figure out how to manage how to solve a problem when, let's say, a chemical industry has some difficulties and need some help. So the idea is, if you consider polydimethylsiloxanes, they have a very low TG of about -120, but the thermostability is not so high. For fluorocarbon elastomers, in contrast, the TG is not low, but the thermostability is high. If you consider some fluorosilicones with a CF3, the TG is good, -65 is good, but the thermostability is not so high because these fluorosilicones undergo some backbiting, leading to cycles, and these cycles evaporate and make a poor thermostability. So the objective here was to combine the use of fluorosilicones and the use of fluorocarbon elastomers in order to lower the TG and to increase the thermostability. And indeed, what happens, the objective was to prepare this kind of fluorosilicones in which the fluorinated group here in the center could make further this silicon atom in order to maintain a good thermostability. Because as I mentioned here, when you have SiO, 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 this undergoes this biting to make this cycle. So if you make this silicon further, you prevent from this biting. So the idea was also to make some side group, fluorinated side group, either C4F9 or this GEM difluoroisopropyl. And so we decided to think about that and to prepare first. Of course, these fluorosilicon were prepared in several steps. The first step was to prepare some diodo compound prior to functionalization. And of course, by stepwise co-thermalization of VDF and HFP, or HFP first and VDF then, it was possible to make some telekinetic diodo compounds containing TFE, because in this case we have a TFE. You recognize here you have TFE. We could use C4F8 or C6F12. And in this case, we have small units of TFE. We have VDF, and HFP, of course, can be maximum P, maximum 2, because as I mentioned before, it's difficult to homopolymerize HFP. And I want to thank my co-workers. They did their PhD in 1994, but this was still from nowadays challenging. And this diodo compound could be functionalized first by ethylation and dehydroiodination to make the divinyl, or by addition onto allyl acetate, and then deiodoacetalization to make diallyl compound. So it was interesting because we have a little spacer, X can be 0 or 1, and in this case, we could introduce by hydrosilation, it was possible to make some new dichlorosilane, so telechylic dichlorosilane, which could be hydrolyzed into disalenol, and either copolycondensed or copolycondensed with this chlorosilane, or homopolycondensed in order to prepare this what is called hybrid fluorosilicones. And of course, we work with Gida, who is an expert in silicon. And in this case, as you can see, we play on R1, R2, RF with different units of EDF, HFP, etc. And the tables of results are here. So it's a non-exhaustive table. We have the different compounds with arete can be C6F12 or even HFP, C4F8 HFP, or even with VDF, C4F4, TFE, one VDF, one HFP. It was not necessary to have a long molecular weight, but it was very important to have a well-designed telechylic compound in order to allow this homopolymerization. And the TG here, we show some melting point. It was not good to have melting point because we want to be elastomeric, no crystallization, in order to favor some cross-linking later. And as you can see, the TG were ranging between minus 18 to minus 53, which was very suitable here in this case. Just to keep in mind that the fluorosilicons commercially available are show a TG of minus 65, 68. So we were a little bit higher, but still the thermostability was very attractive because we could reach very high thermostability even under air, up to 410. And also the state we have oily systems here, in contrast to the first one, which was a little bit crystalline, which gave a solid. So this just an example of TGA thermogram. So this is the silastic from produced by Dow Corning. So you have a decomposition starting from 190 Celsius. This is in the case of these fluorosilicons, we could have a better thermostability up to 380, which is a very good thing with a low TG. So I know this is an example for elastomers. I would like now to speak about surfactants. So you know that surfactants were widely used in many applications for protection of surface, stimulation fluids, or oil recovery, firefighting foams, or as you can see here, paint, lubricant, electroplating, photographic emulsifier, etc. But there is a problem on this, and usually they have they are very efficient, more efficient than hydrocarbon surfactants. So you have a hydrophobic tail with a fluorinated group and a functional group, just like carboxylic acid or sulfonic acid. But these fluorinated surfactants are bioaccumulable, so these stay in the blood. They are toxic and persistent. They are mobile also. They can go in rivers and go in the sea because of the presence of C7F15, which is very stable. And the half-life is about 3 to 5 years, which is incredibly high in the blood of people. So Freon company decided to reduce in the first to have a lower bio concentration factor. But indeed, nowadays, I think that you saw in media that even the polar bears have some what is called PFAS, perfluoroalkyl substances. And when you look at the bioaccumulation factor, this is exponential curve, you can see that increasing the number of carbon, perfluorinated carbon, you are going to increase exponentially the bioaccumulation factor. So we decided to work on co-telomers, with EDF or with trifluoroethylene, in order to see that this can be degradable. And one example was to prepare some mono iodo compound by thermalization of VDF with C2F5I, which was then encapped by ethylene to make a spacer with iodine in order to modify the iodine by alcohol and oxidation to make a carboxylic acid. And as you can see here, this is the surface tension versus the concentration of the surfactant. If you consider the PFOA, this is perfluorooctanoic acid, compared to this surfactant containing 2 units of VDF, we have almost a similar tendency with the same CFC. You have a change of slope here and you have a CFC. So this is very interesting, showing that the presence is not necessary to be perfluorinated, to have all fluorinated here, but to have some hydrogen or carbon. And also by Madix xanthate, we were able also to so we prepared some specific xanthate with a fluorine atom, and we did some raft polymerization of EDF and TFP for low molecular weight compound, which were encapping with vinyl acetate, because vinyl acetate works very well with xanthate. And even the strategy with vinyl acetate and with was a little bit less efficient than the presence of the above reaction. So we can see the change by SEC chromatogram from this mono. Yes.
Sorry for the interruption, but we have 5 more minutes for this session.
All right. And as you know, vinyl acetate is hydrophobic, so it was necessary to hydrolyze under acidic condition, not to favor some dehydrofuranation. So we have a nice results, and even the surface tension of our product was even a little bit similar as that of ammonium perfluorooctanoate. So we did also some work with trifluoropropene. We like this trifluoropropene in radical additions. We make a chemical modification, and then the allyl derivative was reacting by a thiolene reaction in order to bring this carboxylic acid. And as you can see, we could prepare some nice surfactant in which we have a change of curve for the CMC was 0.9 gram per mole. So what happens is, if I want to conclude on this, I have many of the examples, but the time, of course, is, thank you for reminding. And if you look at the different chain transfer agents used in thermalization of VDF, whatever methanol, chloroform, CCl4, this phosphorus containing chain transfer agent, we use also this dibromo compound also to make some macromonomers, this bromo CCl3, this thiol or ICL. You can see that the chain transfer constant change according to the bond dissociation energy. And the higher the bond dissociation energy, the lower the chain transfer constant, showing that these are very efficient chain transfer agents, but you produce low molecular weight. And if you want to design higher molecular weight, of course, you have to find out less efficient chain transfer adducts. So in conclusion, I hope that I convince you that thermalization is a powerful tool to design specific compounds, functional compounds, of course, and then to make some polymers or material. The choice of a chelagen is important, of course. You have to optimize the use of initiator. You have to consider the bond dissociation energy of a chain transfer agent to assess. I didn't mention a lot on the assessment because this is a little bit theoretical. And of course, to use the key function in order to have either monofunctional of telechelix. So you can prepare a lot of different derivatives, macromonomers, telechelix for polycondensation, for polyadducts, for graft copolymers also, because you can prepare a polyacrylate, an anacrylate, which can be polymerized into graft copolymers, or initiator of contraradical polymerization. Okay. So I want to thank you very much for your nice presentation. And also just to mention, if you are very interested by the thermalization of freenated alkenes, we published a book, this is almost 20 years ago, on the well architecture for polymers, synthesis, property, and applications, in which chapter 1 is devoted to thermalization, chapter 2 to telechelix compound, chapter 3 for alternating copolymers, chapter 4 for block copolymers, and chapter 5 for graft copolymers. So thank you very much for your kind attention. I would like to thank all the people who have been involved in this project, okay, and also the supporting, the financial support, whatever CA, French National Agency, Arkema for supplying, of course, DF, and yourself for your kind attention. Thank you.
Thank you, sir. We'll get back for the next session in 10 more minutes at 4:40.
Okay, that's fine. See you soon.
Yeah.